Hello, and welcome to another video lecture for Machine Design ME372. In this video lecture, we are going to continue our discussion of fatigue, and we will work several example problems. We will then get into fatigue based on non-reversed loading. To begin with, these examples, though, are based on what we call completely reversed loading, where the load goes from a tension magnitude to the same magnitude in compression, and we would oscillate around a force or a stress of 0. So in this example here, it's example 6.7 in your textbook, and it says for this step shaft, it is determined that the fully corrected endurance limit is 280 MPa, and that's a great thing to see. Fully corrected endurance limit means SE has already been computed for us. Consider the shaft undergoes a fully reversing nominal stress in the fillet of sigma rev is 260 MPa. So we have an alternating stress of 260 megapascals. And we need to estimate the number of cycles to failure. So to do this, I again like to write down the governing equation that we will use to solve this problem. The expression that we will use to solve this problem is given on page 319 of the note packet, where it is SF is equal to AN to the B. We will replace this SF with the endurance limit SE. If you recall, this expression here is the equation of this straight line portion in the SN diagram. So we will need to be able to compute A and B. And to do that, we can see that we will need to look up the SUT for the material. We were given the endurance limit, SE, and we need to know the fatigue modification factor, script F. And that script F comes from the following table or chart on page 320. The ultimate strength for this problem is 100 kpsi. So I come into the table at 100 kpsi for my SUT, and I can pull off this value here of little f as 0.84, and it's about halfway, about a quarter of the way up. So I would call this 0.845. Going back to our problem now on page 339, we can start to write down all the given information that we have. Here we're given this KF, the fatigue stress concentration factor of 1.55, so we will modify our stress for that fatigue stress concentration factor. We need to note here that even though this says fully corrected endurance limit, it's been fully corrected except for stress concentration factors. And so down here we have modified the stress and increased the stress to account for that stress concentration factor. Now, as we talked about from the figure, we can pull off our fatigue modification factor, our little f. Then we can compute A and B, and now we can come down here and compute N. This is an important equation for you to be familiar with. Here we have solved the expression SF equals AN to the B for N. And doing that, we get sigma rev over A, all raised to the power 1 over B. And this sigma rev here is what we note as the reversed stress, or the completely reversed stress. So in order to come into this equation here, the sigma needs to be a completely reversed stress, or a completely reversed stress equivalent, as we will see when we get to fluctuating stresses. But again, this expression SF equals AN to the B is only good for completely reversed loading. you can't use that expression if you have non-completely reversed loading until it has been modified. So this n equals sigma rev over a raised to the 1 over b then can be used to compute the number of cycles. The next problem we're going to look at focuses on computing the endurance limit and also looking at the stresses. So here it says a 1015 hot rolled steel bar has been machined to a diameter of 1 inch, and it is to be placed in reversed axial loading for 70,000 cycles to failure in an operating environment of 550 F. Using ASTM minimum properties and a reliability of 99%, estimate the endurance limit and fatigue strength at 70,000 cycles. So the key thing here is to compute the endurance limit. So to begin with, in this problem, it starts with the temperature. I typically like to start at the beginning and work with the surface modification and then go through Ka, Kb, and so forth. But here what they're doing is they're modifying the endurance, the ultimate strength, by the temperature, and then moving into the SE. So here it says that we will be operating at 70 F, and that's what the SUT that we have been given in the table A20 is based on, is 70 F, and we will be operating in an environment of 550 F. So we need to modify the ultimate strength based on that temperature. Since the rotating beam specimen endurance limit is not known at room temperature, we determine the ultimate strength at the elevated temperature. So we get our ST over SRT value, and we take the average of the two values that we have given, and we get 0.979. The ultimate strength at 550 then is given by the ST over SRT at 550 times the SUT at 70, which gives us 49 kpsi. Not much difference, but we need to make sure we do adjust for it. The rotating beam specimen endurance limit then, the SE prime at 550, is estimated then to be 0.5 times 49, or 24.5. Now we're ready to go and apply our standard Marin factors. So for the machined surface, we can see that Ka is given by A SUT to the B, and if we look up these values in the table, we'll get A is 270 and B is minus 0.265, so we can compute a Ka of 0.963. This value is less than 1. It's a high value, but a machined surface is a good surface, and so this is an expected value here. For axial loading, we remember that the size factor Kb is equal to 1, and so that greatly simplifies that calculation. From the loading, we know that it's an axial loading and it's a single applied load, and so we have a Kc of 0.85. Now we have already accounted for the temperature, so even though we have temperature effects in this problem, we have accounted for them in our ultimate strength and our SE prime. So Kd is equal to 1. And then for 99% reliability, Ke is 0.814. And since there aren't any other conditions, and we'll use a miscellaneous factor of Kf is equal to 1, the endurance limit can be computed by this expression here. For the fatigue strength, then, we can come and compute our A and our B, and we know that it's operating for 70,000 cycles, so we can get SF at A n raised to the B, and we get 23.9 kpsi. So this would be the fatigue strength at 70,000 cycles. So if we wanted our part to last for 70,000 cycles, we would need to make sure that the stress was not great. Our next example on completely reversed loading is given here by this rotating shaft, and it's simply supported on a bearing on this end at R1 and a bearing here on this end at R2. And we have an applied load here of 6.8 kilonewtons at this location along the length of the shaft. And we are to estimate the life of the part. So the first thing we need to do is determine where the stresses will be critical. And to do that, we draw a shear moment diagram for the beam or for the shaft. In this problem, we can see that our shear would jump up, come over, drop down, come over, and up. And so we would have our maximum moment here at the location of the force, and then we would go linearly from this maximum moment to 0 at the ends. So our shear moment indicates that our maximum moment occurs in this thickest part of the shaft. It indicates here that we have moment at point B is larger than the moment at C. So we know that point B would be more critical than point C because the moment's larger and the diameter of the shaft is actually smaller. So we know MB, that point B would be the critical location compared to point C. However, we're not sure about the moment max here. And in this example, it doesn't calculate the stress. It just kind of assumes that MB would be the critically stressed location. But you need to make sure you actually compute the stress here at this maximum moment, and you compute the stress here at point B in order to determine which one of these two locations is the critically stressed location. It's also important to compute the endurance limit and essentially solve the problem completely for this point here where the maximum moment occurs, as well as point B, because the endurance limit and other factors can be different at this point as compared to point B due to the stress concentration factors and possibly the finish. So we're going to assume that point B is the critical location. But again, if you are given this problem and it's not clearly stated that point B is the critical location, you would need to check both this maximum moment point and this point B. The problem continues by saying, well, we shall solve the problem by first estimating the strength at point B, since the strength will be different elsewhere, and comparing the strength with the stress at the same point. So from table A20, we find that the SUT is 690 and the SY is 580. So SE prime is given by 0.5 times 690. No temperature effects were mentioned in this problem. We can then get Ka and Kb, and all of the other Ks are 1. We will modify the magnitude of the stress instead of using the miscellaneous little kf factor. So down here we will say little kf is equal to 1, and we will modify the stress by the fatigue stress concentration factor. So to find the geometric stress concentration factor Kt, we go to figure A15.9 with D over D equal to 1.1 and R over D to 0.093. And from that, we get big KT, the geometric stress concentration factor, equal to 1.65. Then we can come to this expression here for big KF based on notch length, and we can substitute in KT and are given A and R for this problem. And so we can compute big KF. If this detailed information here was not given, we would go to our table for Q and we would use our expression for big KF as 1 plus Q times KT minus 1, and we could compute this same big KF using that other equation. But here where we know little a and r, we can come and compute the 1.55. The next step is to estimate the bending stress at point B, and so we can do that by computing our moment at point B, which turns out to be 695. And then just to the left, we have the section modulus I over C is given by this expression. So the reversing bending stress is given by KF MB over I over C, and we get 335. So this 335 stress is greater than the SE from up here. So we know that the part will not have an infinite life. We also see that the 335 is less than the 580, so we will not yield, at least on the first cycle. And so from this, we can know that we are in the regime where we can use the expression SF equals AN to the B. So coming and using that expression, we can compute A, we can compute B, and then we can come and get N from sigma rev over A raised to the 1 over B, this important equation again. And we can get 68 times 10 to the third cycles as to for how long the part will live. So this concludes several examples on completely reversed loading. We are now going to jump into what happens with fluctuating loading. But to summarize completely reversed loading, make sure that you are familiar with this expression here, which is used to compute the number of cycles. Make sure you're also familiar with the expression SF equals AN to the B. And that expression is given in the example we just worked previously to this example on page 341, SF equals AN to the B. And then be familiar with all of the Marin factors that we have now talked about. We now want to talk about problems that are classified as fluctuating stresses. So far, we have talked about problems with a loading cycle that looks like this down here, where it's completely reversed. So we would go up to a tension, then down to a compression, back up to a tension, and down to a compression. And the alternating stress would be the magnitude of this curve. So we would go from the zero up to the peak, or from the zero down to the trough. And these two terms would be equal. In this case, we see that this is called sigma alternating. The mean stress is the average stress over time, and so the average stress in this problem would be 0. So that's kind of the definition of completely reversed loading, is your sigma mean is equal to 0, and you have alternating stresses that fluctuate in tension and compression that are equal. So we also have the case of repeated loading, where we apply the load and let it go back to 0. We apply the load, it goes back to 0. In this case, we have a mean stress that is non-zero. We still have alternating stresses that are equal. And then here we have what we classify as the general fluctuating case, where we have a tension load that is applied, and then we have an alternating stress on top of that, where we have what we would classify as the sigma minimum, the sigma min here. We still have our alternating stress components, and our sigma mean would go from the 0 up to the mean of this general fluctuating curve. So you need to be able to be given a curve and identify the alternating stresses, which are simply the magnitudes of the fluctuating component, and the mean stress, which is simply the average stress over time. So again, the problems we have talked about to date so far have talked about completely reversed loading. We're now going to develop expressions and equations for these types of cases and fluctuating stresses. To define a few terms here, we're going to use this general fluctuating curve, and here we've blown up the curve on the previous page where we have a sigma min, we have our sigma mean, and we have our sigma a's. This sigma r is simply the range from the peak to the trough. So sigma mean is given by the maximum stress plus the minimum stress divided by 2. And that's how we can come and compute sigma mean. We'll take the maximum value here plus the minimum value here and average those two numbers. To compute the alternating stress, we take the maximum value here and we subtract the minimum value, and then we divide that by 2 to get the alternating stress component. And the way we solve these problems is to break them into the mean and the alternating components and essentially solve two problems. The failure envelopes for these curves is given on this page here. This is kind of a busy curve, so let's look at it carefully. Here on this x-axis, we're plotting the mean stress. Here they have called it the mid-range stress, and that's another name for sigma mean. I call it the mean stress. Here it's referred to as the mid-range stress, but it's the same stress. So on the horizontal axis, we plot the mean stress component. On the vertical axis, we plot the sigma A, or the alternating stress component. And these lines here represent various failure envelopes. So if we come over here and we go to the yield strength on the mean stress, and we go to the yield strength on the alternating stress, this dashed line, which is a straight line between those 2 points, represents the yield line. So if I had a zero mean stress and it was completely alternating, the maximum stress that could be before I yielded would be the SY. And the same down here, if I had zero alternating stress, the maximum stress I could have for a mean stress before I yielded would be SY. So this dashed line represents the failure line based on yield. Now these other curves represent failure based on 10 to the 6th cycles. So in the SN diagram, we looked at the range between 10 to the 3rd and 10 to the 6th cycles. And we were able to look at SF equals AN to the B. In general fluctuating stresses, no longer do we have a curve that really shows us an SN diagram. But this curve right here is based on failure at 10 to the 6th cycles. So if we are going to fail, it's based on 1,000,000 cycles. If we look now at these individual curves, we can look first at this line here that goes from the endurance limit to the SY, and that's the Soderberg line. And so if you had a zero mean stress, the maximum stress that could be applied in your alternating stress would be the endurance limit before you failed. If you had a zero alternating stress, the Soderberg curve says that the maximum stress you could apply would be the SY. Now typically what happens is we have some alternating component and some mean component, and if we are inside of this line, we will have a safe design. If we are on the outside, out in this region here of the Soderberg line, then we would fail. So for example, this point A shown here at SA and SM would be a failure in the Soderberg curve, but it would not be a failure in the modified Goodman line. Goodman goes from the endurance limit out to the SUT. And so you can see the mid-range stress, the mean stress, is based on the ultimate strength failure, not a yield failure. And then we have two other curves. This one here is called the ASME elliptic line, and here we have the Gerber line is this curved line here that also goes to the SUT. These expressions down here are the equations of these curves. So for the Soderberg, we have sigma A over SE plus sigma M over SY is equal to 1 over N. If we let N here be 1, then we get the equation of this straight line. Sigma A over SE plus sigma M over SY would be equal to 1. We can see that to change this expression for the modified Goodman line, the only thing that changes is we change the SY to SUT. Other than that, they're the exact same expression. Then to get the Gerber line, all we do is we square the mean component term. And it's important to note here also that the safety factor is distributed now through the mean and the alternating stress components. So we take this little n and multiply it over here on this side of the expression, and then we square the mid-range or the mean stress component to get the Gerber line. In the ASME elliptic curve, we square both quantities and we change the SUT back to SY. So these equations are all very similar, and their lines are fairly similar. It's important that you know the differences between these curves and that you can write down these failure curves. You need to have these failure curves memorized so that you can solve the problems. So again, this is a very important curve and one that you need to be able to draw and understand. And we plot the mid-range stress on the horizontal axis, the alternating stress on the vertical axis, and then we plot the SY and the SUT, and here we plot the SE and the SY, and we get these failure envelopes. And if our stresses are such that we're on this side of the failure envelope, we're safe. If we're outside the failure envelope, we fail. What we typically do is we come and we have a load line for the particular problem. In this case, it's showing that our load line here starts at 0 and then propagates out at this slope of SA and SM. And this would be a failure curve, and we could see where we intersect our failure line. And where we intersect our failure line, we call that the SA and the SM instead of sigma A and sigma M. Otherwise, this is sigma A and this is sigma M. So these sigma A and sigma M, these are just points